So Rafael Bravo will present a new soft theorem for single field inflation. You remember you have 15 minutes and 5 for question. I will let you know when you have 5 minutes left. So
Okay.
go ahead.
Can you see my cursor?
Yeah.
Yeah. Okay. So hi everyone, and thanks to the organizers for giving me the opportunity to speak here. So in the following, I'm going to talk about this work that has been in collaboration with my advisor, Gonzalo Balma, and it's mostly related to primordial no-Gaussianity in the context of single-field inflation. So as motivation, I always like to show these two pictures, but I'm almost sure that most of you know what is inflation and what is cosmology. But I always like to emphasize the role of fluctuation in this history. So in this picture, we have two images of the universe at two different times. And what is common here is that we have a background with little fluctuations. Here in the fluctuations in this image here are galaxies that are as a matter fluctuations, and in the cosmic micro background we have temperature fluctuations. So basically, cosmology studied the origin, evolution, and the possible fate of this synchronization experiment that we call the universe. And the fluctuations are an important play an important role here. So concerning the origin of the universe, uh, we know that that inflation plays an important role there, but nowadays nobody knows the actual action for inflation. So we need some hints to construct this action. We need hints obviously from observation, from the cosmic microwave background, from large scale structure surveys, and now from gravitational wave surveys. But we also need to keep in mind the theoretical physics hints. For instance, the particle physics, OB compression of gravity, for instance, the Swampland conjectures, and so on. So typically, models of inflation predict several observables. For instance, the tensor to scalar ratio, the spectral index, but only another important thing is this parameter FNL, which tell us about the generator of non-Gaussianities. So what is important here that the parameters shouldn't be conflict with either observations nor theory. And also it's important to do model independent results. Okay, let me review basically what is inflation, and I would like to introduce the ingredients to explain what we did. So inflation basically is the shrinking of the Hubble sphere. This is the Hubble sphere, defined as A times the Hubble parameter to the minus 1. We are going to have inflation as long this parameter epsilon remains smaller than 1. This is the so-called first slow roll parameter. So in order to have the simple model of inflation, we need to introduce a scalar field minimally coupled to gravity with a slowly rolling down potential. So this is typically the behavior of the potential, and you can find hundreds, if not thousands, of potential that satisfies this slow rolling condition. And if you apply this slow rolling condition to the Klein-Gordon equation for the scalar field, we have the so-called slower approximation that has attractor solutions. By attractor, I mean in the phase space, you have an attractor. Right? So this is concerning the background part. But here, the most important thing is the fluctuations. And to deal with fluctuations, we typically we use the ADM formalism, in which we turn off this fluctuation and we move it to one of the scalar degrees of freedom of the metric. And here I introduce this field. This is the so-called curvature perturbation of, if you want, the primordial curvature perturbation. And after solving the action for the ADM variables, we can replace them back, and we can find a perturbative action for these fluctuations. This is the second order action for the fluctuations, and after imposing a bunch Davis initial conditions, we can have this. We can find this behavior for the fluctuations. So this line here is what is called the horizon that I showed before. So inside the horizon, the perturbations can oscillate, but in order to satisfy an adiabaticity condition, when the perturbations excite the horizon, they have to remain constant. This actually is a theorem proved by Weinberg. This is the so-called adiabatic mode condition. So, but the most important thing here is how we can connect the perturbation with observation and with, sorry, this is another picture of the behavior of the perturbation inside and outside the horizon. We can always split the modes between in the short contribution and the long contribution. A long mode here is defined as a mode that has a wavelength larger than the side of a horizon. So in order to obtain information from the perturbations, we need to compute correlation functions. And for instance, we can compute the 2-point correlation function using basic quantum mechanics. And then we can parameterize the power spectrum in this way, given by this scalar amplitude and the spectral index. The spectral index is a number that has been well measured. For instance, this is the last measured by the Planck collaboration. But what is important for this work is the 3-point correlation function that defines the bispectrum. And in particular, I'm interested in this limit of the 3-point correlation function, which is called the squeeze limit. And this defines the so-called FNL local parameter. So, but the bispectrum is not so straightforward to compute, since we need to deal with nonlinearities. And actually, the first person who computed correctly the bispectrum was Matasanas back in 2003. So we need to compute the cubic order action. Then we put the Hamiltonian that we can obtain here in the informalism equation, and then we can compute the 3-point correlation function. And here you can develop something like a kind of a Feynman diagrams for cosmological correlators. That the difference here is that we are evaluating the correlators in the same time. So this is why the formalism is called the in-in and not the in-out, the difference from quantum field theory. And in this way, there are some people that have developed interest in formalism to only study the fluctuations. And for instance, there is this ongoing research program, which is the Cosmological Collider, developed by Rafael and Matasanas. And in the last couple of years, we also have this program developed by these people that we can obtain correlation function without the need of a Hamiltonian. This is the philosophy of the bootstrap. So, but for the 3-point correlation function in the squeeze limit that I showed before, we have the following result. And this is the so-called Matasanas consistency relation that tells you that the 3-point correlation function is completely determinate in terms of the power spectrum. Here you can read that this correlation is a kind of soft theorem, because you can remove this mode with a large wavelength. So, sorry, this is the prediction for the parameter FNL. Sorry. So this is the prediction for these parameters, and is a quite small number, something like 10 to the minus 2, and this is the current constraint that we have from CFB observations. This parameter can also be constrained from large-scale structure and CMB spectral distortions. Here are an incomplete list of reference of works related to that. So, but what is important of this relation is basically that tells us that how two short modes, namely K1 and K2, are modulated by a long one. And this is a crucial test for all single field attractor modes of inflation. I mean, independent of the potential, you can, if you assume the slowly roll condition, you can always going to obtain this form for the bispectrum in this particular limit.
5 minutes.
So, 5 minutes. Oh, sorry. There is a nice way to obtain this relation from symmetries that was developed by people like Criminelli and Saldarriaga. Basically, you know that the action and the metric is invariant under this symmetry, and then you can use this to compute the 3-point correlation function, and you will find this result. So this procedure is known as the background wave method. Here you can infer that the Matasanas consistency relation can be understood as a soft theorem that emerged by exploiting the invariance of the line element under this diffeomorphism. So can we trust a result that can be obtained by using a particular choice of coordinates? Of course not. And I'd like to share this phrase by Stephen Wyvern. You can use any coordinate that you like to describe a physical system. If it shows the wrong ones, you will be sorry. And actually, this result is what people call a gauge artifact because we can remove it by a changing of coordinates. So the actual prediction for single field inflation is that the primordial bispectrum in the squeeze limit is actually 0. Okay, but something happened with another model of inflation that we can have, for instance, in the potential exactly flat region. When you have an exactly flat region, something weird happens to the perturbation. The perturbation starts growing outside the horizon. At first view, this can violate the Weinberg-Soft theorem, the Weinberg-adiabatic theorem, but actually does not violate the theorem. The model is actually adiabatic. People in the last year have been using this feature to enhance the production of primordial black holes. And this is an incomplete list of reference. But what is important here is that if you have a phase like this in single field inflation, you will note that the bispectrum is quite large. Yes, you are going to have this number, and this is an explicit violation of the Matasanas consistency relation. So, can symmetries tell us something about this result? Of course, that they can. That's what we did. So we know that the action and the cubic occular action and the metric are invariant under this non-trivial transformation. And here we can note that the long mode is no longer constant outside the horizon, so it has no dependence on time. And now we have these two new functions, C naught and alpha, that are determined by this function A. That is a function of the slow roll parameters. So here n is the number of if we define it in this way. The first few terms of A are defined are this one. So we can also find a relation between the short mode and the full mode of solution of the equation of motion that is modulated by a long mode in this way. So using this, we can compute the bispectrum in the squeeze limit as the same way that I showed before, and you will find this relation. So here you will find the Matasanas consistency relation plus this correction, or not? It's not a correction; it's another part, the non-attractive part, which is dominated by the function A, that is function of the slow roll parameters, and a derivative of the power spectrum. And this is what we call that is a new soft theorem. So to test it, we use the fact that this stage of inflation, when you have the constant potential, is characterized by having a large second slow roll parameter. In that case, the function A takes this form. So additionally, the power spectrum in this model takes this form, and if you plug it back again, you will find the desired result. We can say that this also is a gauge artifact again. So the FNL parameter for this model of inflation is also 0. So my conclusions. So we have generalized this well-known Gaussian consistency relation for models of inflation where the curvature perturbation evolves outside the horizon. For both models, we can infer that the modulation of the small ball by long ones can be understood by a result of asymmetry, and actually this symmetry is what people call residual diffeomorphism that give rise to this new soft theorem. And what is important is that the observable squid bispectrum vanishes at leading order for attractor and non-attractor models of inflation. So, and this is the most important thing here. If, for instance, if tomorrow we measure a sizable amount of non-Gaussianity in this squeeze limit, from where does it come from? multi-field model of inflation, non-Bunch-Davids, vacuum initial conditions, non-canonical terms. This is an open question nowadays. So thanks for your attention.
Thanks to Rafael. So this is time for questions. Mauricio.
Yes, thank you, Alex. Congratulations, Rafael, for your talk. It was so nice. I have a little question related with the FNL parameter. When do we expect to have some experiment that can measure this parameter in a better way? So as I understand, that it is within the confidence level, but it has a huge error bar. So when
the final parameter, it's only constrained. So here you have the number, the zero,
yeah.
you have the 5/2 of the fake half of ultra slow roll, but it's quite a poor measure. So in the following years, there are experiments that can constrain this number in a much better way. From CMB, we are waiting for the CMBS4 generation of service. We can also constrain this number from LSS surveys. For instance, the new Vera Rubin telescope can constrain this number in some way. And also from CMB, but not by looking at temperature fluctuations. Instead, we can measure the energy spectrum of this black body radiation. In some way, that is related with the chemical potential. The chemical potential can be related with the parameter FNL.
Okay, thank you.
Is there another question? Francisco Rojas. You're muted.
You're muted.
Always the same. I'm sorry. Yeah. Thank you, Rafael. Thank you, Alex, for letting me know. Quick question, Rafael. The correction that you guys found for the Matasanas condition, is it smaller? Is it small in some sense? Is there some parameter? Parameter.
It depends on the model, because
okay.
Principle, you have this function here A which is function of the slower parameters, and typically the slower parameters are small. But in this scenario, which is called ultra slow roll inflation, you can have a large second order slow roll parameter. So actually, in this case, the contribution from the correction is larger than the Matasanas contribution.
Oh, I see. Okay. Okay, thank you.